Okay, let's go ahead and take a look at section 2.3 now in your book on instantaneous velocity. Say versus average. Up until now, we've considered just a general definition of average velocity. It's just the average rate at which an object's position changes during a certain time period. Now, for a few situations, that's all that's needed. But if the object's velocity is itself changing within that time period, we'll find it useful to consider how fast the object is moving at a point in time, not just over an interval of time. Now you'll find as we progress through our development of various equations and physical laws that the velocity an object has at a point in time is often much more useful than just an average velocity. More on that later. For now, let's just take a look at some various ways to quantify instantaneous velocity. Now this is where my general physics course and my calculus-based physics course will diverge a bit. I'm going to start with a general means to determine instantaneous velocity that all students in all courses can use, and then I'll include some extra discussion on a calculus approach for those in AP Physics. Now, anyone, of course, is free to view that portion, but sometimes the mathematical notation itself can get a bit awkward without formal calculus instruction. Okay, enough background. Let's go ahead and begin. Now, if we produced a graph of position versus time, our math classes inform us that the slope of a line on such a graph represents the velocity, or rate of change in position, as we've defined it. Now, in the graph that you see here, you see the red curve. Well, it's just that. It's curvy throughout. There are no straight line segments of this graph, which means that the velocity of this object is constantly changing. Now, if we wanted to determine the average velocity of the object, maybe between points P1 and P2, we could certainly do that. We could just construct a line connecting those 2 points and then measure the change in the x position, measure the change in the time, and just take that ratio and get the average velocity over that time interval. Now you can certainly see by looking at the red graph that not only is it below the black graph, that really doesn't have anything to do with velocity. Velocity is related to the slopes of these lines. What's most important is to see that in the first half of this portion, you can see that the red line, at least in general, seems to have a shallower slope than the black line. And in the second half, it's steeper. So clearly, we have some changing velocity here. Let's go ahead and see if we can figure out how we can get the instantaneous velocity at a point in time, not over a point in time, not over a time interval. So on a graph of the particle's position versus time, the instantaneous velocity is the slope of the tangent to the curve at any point. And the way to approach that is if I were to take smaller and smaller time intervals, instead of going all the way from T1 to T2, if I were to shrink that and make it a smaller time interval, I'm going to start getting a slope of a line connecting those 2 points that is actually closer to the slope of a line tangent to that red curve at that point. Now there are some, so we need to consider smaller time intervals. That's the key idea here. So sample the object's motion at a shorter interval of time, and you'll get a better sense of what the object is doing within that time interval. Okay, now there are some approaches, and I'll do this in the next slide, where we can use some calculus to get to that point. But for anyone in any course in physics, just understanding what the slope of a line tangent to a position time graph represents as instantaneous velocity, that's a useful skill. Now, let's take a look at this road trip down here for a moment. I have a train and a car that are both going from the same position. They start at position 0. They end about 10 miles away, or at least that's the last point at which we graphed its position, their position. We see they're 10 miles from the starting point, and it took about 10 minutes. You can see the train has a nice little straight line segment here on a position time graph representing constant velocity. You can see the car is variable throughout. I want to ask you if you can determine the average velocity for each of these two objects during the trip. Are there any times at which they are side by side, and any times at which they might have the same speed? Now again, this is to give you a chance to practice this. I'm going to suggest that you pause the video and try to answer these questions yourselves, and then when you're ready, come back and take a look at it. Now let's take a look at the average velocity. You can clearly see that the average velocity of the trip for both objects is in fact the same. So average velocity, again, is just defined as a change in position divided by time. We see that they both traveled 10 miles. It took them 10 minutes to do so. And we get 1 mile per minute, or 60 miles per hour, and I'll leave it up to you to confirm that those are the case. But number 2, any times at which they are side by side. You can certainly see that the train starts out getting ahead of the car. Certainly the train is not obstructed at all by traffic, and so it can set its speed at a constant rate and maintain that. So in the beginning, the train is certainly ahead of the car. They do meet up right around this point here. That's where the car sort of catches up for a brief moment, and that looks like it's about 6 minutes. Just approximate. And again, it looks like now the car is ahead of the train. The train starts to overtake the car there. It looks like at a position maybe a little bit, or a time rather, a little bit of about maybe 8.1 minutes, somewhere in that area. I'm just going to round it to 8. It's close enough. And then, of course, right at the very end, at 10 minutes. And now this last question, which is what this slide is really about. Are there any times at which they have the same speed? So the engineer on the train is looking at the speedometer of the train. It always reads 60 miles per hour. In the beginning, we can see the driver of the car would notice the speedometer reading less here, but it looks like right around here, I'm going to change this up here to a different color, maybe right around here, we get a point where the slope of a line tangent at the curve is about the same general shape as the train's curve, and we would say that occurs maybe at about 1, 2, 3, I'm going to say right around there, maybe almost 4 minutes. So at about the 4-minute time interval, the car and train have the same speed. Now as I continue on and look through here, I can see that another time interval occurs or point in time rather, occurs right around here. We see that occurs at around 7 minutes. And perhaps one more right around here. And that's maybe a little bit beyond 9 minutes. So let's just call that 9.2 minutes. Okay, so there we go. Graphs are useful. They help us understand relationships between variables. In this case here, a graph of position versus time can give us a sense of the velocity. Sometimes we can get average velocity, and other times we can get instantaneous. Again, both of those are useful at various times. You'll find that instantaneous velocity is actually quite a bit more often used in our class than an average value. Okay, now that completes the general discussion on instantaneous velocity that everyone can use. This next slide is going to get into some calculus, and so again, feel free to watch this if you like, but for AP Physics students, you need to have this. The instantaneous velocity is the average velocity in the limit as the time interval becomes infinitesimally short. You certainly use that kind of language in your calculus class. If you haven't taken calculus yet, if you've taken that concurrently with this course, you'll certainly use that language quite a bit. So the limit as the time interval becomes infinitesimally short, and that's essentially what we're doing here. Go back to this one. As I consider smaller and smaller time intervals, as I'm doing over here, if I take the limit of delta x over delta t as the time interval shrinks, that ratio will approach a particular value. And calculus provides us the means to actually quantify that value if I can write position as a function of time. And so you will see this kind of notation. If you've been through calculus, you've certainly seen this quite a bit, so much so that we probably have not continued to write the limit as delta t approaches 0, or the ratio of delta x over delta t. You probably have gone right from instantaneous velocity is equal to dx dt, just means the time rate of change in position, and that's on an instantaneous value as opposed to an average value. Okay, and again, that notation can be a little bit confusing. There's a lot of calculus theory that allows you to go from here. Okay, and so I'm not going to spend time going through this here. That's I'll leave that for your calculus class. But that is that whole mathematical framework really allowed physics to progress quite a bit beyond what we were able to do when all we considered average values. So very important part of physics as well. Now, since this is a video lecture, I'm not going to share this story with you. Again, if you would like to hear about it, be sure to ask me in class. Ideally, a speedometer would measure instantaneous velocity. In fact, it really measures average velocity, but over a very short time interval. So if you think about it, the ability to measure the instantaneous rate of change in something physical, like your car's speed, it really cannot be done at an instantaneous value. Okay, we rely on calculus to provide some mathematical means to take that limit as delta t approaches 0. We can't actually do that in practice. So the speedometers, they just measure average velocity, very, very short time intervals, and that's is close enough to an instantaneous value that that we can rely on it. Now, note that the derivatives of various functions are studied in calculus. This book does give a summary in Appendix B. You will find that when you take the AP physics test that you really don't need to memorize the derivatives of various functions. You'll be given a table of both derivatives and integrals that you're allowed to use. That's not the case probably in your calculus course, but certainly here our goal is to understand the physics, not the calculus. We're using calculus as a tool now, so you'll have access to derivatives and integrals when you take the AP physics test. We need to know how to use them. The derivatives of polynomial functions, which we use a lot, is fairly straightforward. Maybe getting a little bit ahead of the calculus course if you're taking it now for the first time. But if I can write position as a function of time, as sort of shown here, and I want to take the derivative of that position with respect to time, if I have a constant times t to the nth power, the derivative just is simply going to be c times n times t to the n minus 1. And again, if you're in if you've been through calculus, this is probably secondhand for you. If I have a constant, if I take the derivative then of that constant with respect to time, constant means it's time invariable. It doesn't change with time. So the derivative, or rate at which that constant changes as time continues, is 0. Okay, and so there we go. I'm going to go ahead and stop this video here as sort of theory. I'm going to put a couple of other videos out there, show you how we might be able to use this in practice, and then certainly we'll practice this concept in class. So there we go. That completes this video on instantaneous velocity.